In this lecture, we are going to talk about cosmic ray muons and their applications. We'll start off by first presenting a motivation for doing research in this area of science. This will be followed by an introduction to cosmic rays. Now, as you all know, that physics is basically an experimental science. Whatever new knowledge that we gain is based on the experiments that we perform. And as an example of a cosmic ray experiment, I would describe the Grapes 3 experiment, which is done in Ooty in southern part of India, about 1,000 kilometers south of Mumbai. And in this experiment, there are a number of institutions that are involved, including those from India and Japan. To perform an experiment of significance, it is important to have instrument which can make measurements which are better than what has been done before. And this is very important in science. For example, if we were to use the same instrument as is being used by others, we would find the same facts as those found by others. And research is all about finding new facts or discovering new phenomena. So a very important component of experimental science is development of new technology. So the next topic that I would dwell on will be the technology development for the Grapes 3 experiment. And finally, we would conclude by describing some of the scientific results, and especially one result that has enormous societal applications. So let's turn to the motivation for doing research in cosmic rays. As you know, every star, galaxy produces radio waves or light or X-rays or gamma rays, which are collectively known as photons. But these photons themselves are produced in interaction of high energy charged particles. The highest energy particles that exist in nature are known as cosmic rays. Though named cosmic rays, but in reality, they are mostly protons and some charged nuclei such as helium, carbon, nitrogen, etc. An understanding of any phenomena in high energy astrophysics therefore requires that the sources of cosmic rays to be understood. To give you an analogy, charged particles are like the engine that drives the high energy universe, and photons that are emitted basically are like an exhaust from the engine. So if you want to understand the engine, you have to understand the charged particles. Now, there are 10 raised to 11 galaxies that constitute the visible universe. By using galaxy as a unit, let us explore what constitutes a galaxy. Our galaxy, for example, contains 10 raised to 11 stars with vast amounts of space between them, that is known as interstellar space. So what fills the interstellar space? Well, it is permeated with magnetic field, gas clouds, dust, black body radiation, starlight, and of course cosmic rays. If you now examine energy density of these components are, for magnetic field, kinetic energy in gas, starlight, black body radiation, and cosmic rays, all are approximately 1 electron volt per cubic centimeter. It seems there is an equipartition of energy. We do not know what the reason is, but this is an observational fact. Now, we know all the other components play a very important role in the evolution of our galaxy, and we expect cosmic rays also to play a role. The highest energy particles that are produced in man-made accelerators at present are at CERN, where energy E equal to 8 times 10 raised to 12 electron volt is achieved. On the other hand, nature reaches energy as high as 10 raised to 20 electron volt, which is nearly 10 million times higher than what we can do on Earth with our most advanced technology and capabilities. Nearly 1,000 of these particles strike Earth every single day. So the question arises, how does nature produce these particles and how does it accelerate them to such high energies? To give you an idea of what these energies mean, for example, ordinary light through which we see each other has energy between 2 and 3 electron volt, and nature on the other hand produces such high energy particles that are even difficult to imagine. Now let's go through a brief introduction to cosmic rays. Cosmic rays are the highest energy particles produced by nature, as we saw just now. Cosmic rays have been observed over an extraordinary range of energies, going all the way from 10 raised to 8 to 10 raised to 12 electron volt. Cosmic rays below an energy of 10 raised to 12 electron volt are usually detected by space-based instruments, and those above this energy are detected by ground-based detectors. Cosmic rays, as we saw, are mostly charged particles of various nuclei, with protons constituting approximately 90% of them, helium nuclei about 7 to 8%, and rest of the heavier nuclei no more than 2 to 3%, and electrons and photons are about 1%. So in summary, cosmic rays are energetic charged particles with a very good representation of the entire periodic table. As I already mentioned, physics is basically an experimental science, and therefore any progress in understanding of cosmic rays would require instruments to precisely measure their properties. Due to huge energy range of cosmic rays, a variety of experimental techniques are used for their detection and measurement. Let's talk a little bit about the history of discovery of cosmic rays that were discovered nearly 106 years back on 7th August 1912 by Victor Hess aboard a hot air balloon using very simple instrument. This actually set the explorer tradition for future experiment. Now here is an interesting contrast. Unlike most branches of physics, where experiments are done in well-maintained and nicely equipped laboratories, most of the cosmic ray experiments are done at diverse and very remote sites all around the Earth and sometimes even beyond. So below I give you a very partial list of some of these experiments. As you can see, there are experiments being done at sea level, on mountain altitudes. For example, the Grapes 3 experiment in Ooty is located at an altitude of 2.2 kilometers above sea level. And then there are experiments being done underground. In fact, in India, there was an experiment done nearly 3 kilometers underground, which unfortunately is closed now, in Kolar Goldfields near Bangalore. And then there are experiments being done underwater, under deep lakes and Atlantic Ocean. There are even experiments being done under the polar ice cap in Antarctica, the so-called ice cube experiment, which is a cube of 1 kilometer by 1 kilometer by 1 kilometer. Then there are experiments being flown on stratospheric balloons to altitudes as high as 35 kilometers above sea level. And then, of course, there are experiments in space. For example, the AMS experiment on International Space Station at an altitude about 200 kilometers. Then there are experiments 1,000,000 kilometers away from Earth. And there are even experiments where instruments are more than 100 astronomical units away from Earth. That's in interstellar space. Some of the early experiments were done on ships going around the Earth, on aircraft flying at high altitudes, etc. So there is an interesting prerequisite to be a cosmic ray physicist. You have to be adventurous, and you should not mind venturing out beyond the safety of your home institution. Now let's recall some of the experimental facts. Number one, cosmic ray flux is constant in time, so it doesn't matter when you make an observation, you will receive the same number of cosmic rays per unit time. It's also isotropic, which means it doesn't matter which direction you look at, you find the same intensity of cosmic rays. Now it is already established that in the energy range between 10 raised to 14 to 10 raised to 16 electron volt, the cosmic rays are produced well within the galaxy, that is Milky Way, and higher than this possibly come from extragalactic sources. Now in the galaxy, galactic magnetic field in gas clouds in the interstellar space has random orientations which deflect cosmic rays particles, completely randomizing their direction. So, the cosmic ray motion, instead of being in a straight line, becomes one of diffusion and causes the flux to become isotropic and constant in intensity. And below you can see a reference which gives a great detailed account of the physics of cosmic rays by these authors. Next is a very important topic. We mentioned that magnetic field plays a very important role, and the most important role it plays is in trapping cosmic rays. You see, normally the cosmic rays should escape the galaxy in about 10 raised to 5 years, but they are known to reside in our galaxy for as long as 10 raised to 7 to 10 raised to 8 years. That's nearly 100 to 1000 times longer than what it should be staying within the galaxy. And this happens because of magnetic bending, which is known as trapping. And this trapping actually causes the intensity of cosmic rays to rise, but because of randomization of direction, we lose all sense of the direction of sources where they were produced, because they seem to come with equal intensity from all directions. So, this is one limitation, but there is significant addition of information which is based on the sources of cosmic rays and the medium through which it has propagated, and this information is contained in the energy spectrum of cosmic rays and their composition in terms of various nuclei. We can still learn a lot about sources of cosmic rays by actually studying the gamma ray flux, because gamma rays being neutral come straight from the source of production to their detection at Earth. Let us look at some of the other properties of cosmic rays, and one of the most important one is the energy spectrum of cosmic rays. Now, on the screen you see two plots. The one on the left shows the energy spectrum of cosmic rays, where on x-axis you see the energy in electron volt, and it goes all the way from 10 raised to 8 electron volt to 10 raised to 20 electron volt. And on y-axis is the flux of cosmic rays in units of per unit area, per unit time, per unit solid angle, and per unit energy. But what you should notice is the scale is not linear but logarithmic, and the y-axis, the flux varies by 32 orders of magnitude, and the energy on x-axis varies by 12 orders of magnitude. So, it's such a large range that we can only present it by using logarithmic scale, and that is expressed by this equation n greater than e equal to k times e to the power minus gamma. So, if it is a power law spectrum as the one shown here, and you take log on both sides, you get a straight line, and that is how the cosmic ray spectrum appears when we measure it. Now, I want to draw your attention to a couple of features of this spectrum. If you look at 10 raised to 10 electron volt, the number of particles that we receive is 1 particle per meter square per second. So, if you had a detector of a square meter, you will record 1 cosmic ray every second, and that is more than enough for you to collect enough data, let us say in a duration of about a month or so. But if you go to higher energies like 10 raised to 15 electron volt, the flux drops to 1 particle per meter square per year. So, obviously, 1 square meter detector is not sufficient. You need detectors which are tens of thousands of square meter in area, and obviously those detectors have to be placed on ground. They cannot be flown in space. And if you want to go to still higher energy, let us say 10 raised to 18 electron volt, the flux drops very rapidly to 1 particle per kilometer square per year. So, even a square kilometer is not enough. So, there are experiments being done with area exceeding several thousand square kilometers. On the right hand side, you see another plot which shows the energy spectrum of individual components such as hydrogen, which is nothing but proton, helium, carbon, iron, etc. And you see the spectra look very similar. They have same slope, but their contribution to cosmic ray flux is very different, which is listed here. So, now let us turn to another important topic, that how does these particles acquire such high energies, that is the acceleration of cosmic rays. Now, we all know charged particles can only be accelerated by changing magnetic field or electric field. So, there are two well-known mechanisms that are proposed. One is called betatron acceleration, where particles are accelerated in a homogeneous magnetic field, which is increasing with time, and if the particle leaves the acceleration region before the field decreases, you will gain energy. This condition is known as adiabatic constant here. And second is Fermi acceleration, where acceleration in collision with magnetic clouds leads to gain in energy, provided it is a head-on collision. The cloud is moving towards the cosmic ray particle, and it loses energy when it is moving away from the cosmic ray particle. So, this mechanism is not very efficient, but a modification of Fermi acceleration, which is known as Fermi acceleration of second order or stochastic acceleration, is a very interesting one, and most probably that is what works in nature. So, here what happens is soon physicists realize that a head-on collision is more likely than a overtaking or passing collision, and therefore, the probability of gaining energy is higher than the probability of losing energy. Unfortunately, the energy gained is proportional to u square over c square, where u is the velocity of cloud, which is not very large, and c is the velocity of light. So, the energy gained is very small, but it is always a net gain in energy that happens in this case. However, if this gain in energy can happen repeatedly, which happens in certain circumstances, then you can gain sufficient energy. But what is most remarkable is that this mechanism leads to a natural power law spectrum of cosmic rays. The mathematics of it is shown here in brief. You can go through it in detail in a reference which is quoted just at the bottom of the slide. Now, what are the sites of cosmic ray acceleration? One of the most popular sites is supernova shocks, which are produced in supernova explosions and their remnants, and these can accelerate particles to extremely high energies. And what is nice about this mechanism is that the rate of supernova explosions in our galaxy and the energy that they generate is enough to account for all cosmic ray flux that is present in our galaxy. Of course, it is also proposed that acceleration could happen in other compact objects such as pulsars and X-ray binaries, etc. Next, let us turn to the interaction of cosmic rays in our atmosphere and the production of extensive air showers. Now, when we talk of atmosphere, normally we think of a transparent medium in which we breathe oxygen and we survive. But as far as cosmic ray particles are concerned, atmosphere just acts as a big, thick absorber. Now, we all know the atmospheric pressure at sea level is 76 centimeters of mercury. If you multiply that column height by density of mercury, which is 13.6 grams per cubic centimeter, you get about 1000 grams per centimeter square of mass. So, the atmosphere is essentially equivalent to a mass of 1 kilogram for every square centimeter area, and that is what the protons experience. So, when a proton enters that Earth's atmosphere, it interacts, and that interaction is shown by an equation here. Proton interacting with, let us say, a nitrogen nucleus produces secondary particles which are known as pions, and there are three varieties: pi plus, pi minus, and pi 0. The charged pions decay to produce muons of same polarity, and pi zeros decay almost instantaneously to produce two gamma rays. Gamma rays, as they propagate further down, can interact in the electric field of nucleus to produce a positron-electron pair by a process known as pair production, and subsequently these positrons and electrons can radiate a photon by a process known as Bremsstrahlung. By using these processes, well-known Indian physicist Homi Bhabha developed the theory of production of showers, which is still used today. So, essentially what you get is, from a very high energy particle that you get at lower altitudes, electrons, positrons, and gamma rays, which are known as electromagnetic component, which constitute 90% of this shower. And then there is muon component, or also known as penetrating component, which is about 8 to 10% of the shower particles. And then there are pions and another kind of particle which I have not described, kaon, etc., These are called hadronic components, and they constitute only 1% of the particles, but they carry large fraction of the energy of the shower. And then there are also neutrinos produced, which of course largely pass through the earth without being detected. Now, for a proton of given energy E, the number of particles that are produced at any given level n is proportional to the primary energy E. For example, at UT, which is at 800 grams per centimeter square into the atmosphere, we typically produce for a 10 raised to 14 electron volt proton about 20,000 particles, which are spread over 1,000 square meter. So, if you want to study such phenomena, you need detectors which are thousands of square meter in area at least. Now, the information on electromagnetic particles in terms of their density and arrival time provides us information on the energy and direction of the primary particle. Now, energy is important because you want to measure the energy spectrum, and direction is important because if you want to do astronomy, you need to know the direction of the particle that you are detecting. Number 2, the muons are a very important component of cosmic ray showers because they contain information on the nature of this primary particle, whether it was a proton or a heavier nuclei. That is something you can determine by counting number of muons. It also allows us to discriminate between gammas and protons, primaries. Muons are also sensitive to solar and atmospheric phenomena, as we would see later. Now, let me turn to the GRAPES 3 series of experiments. The GRAPES 3 experiments began in mid-60s, nearly 50 years back. We started with the GRAPES 1 experiment, which ran for nearly 20 years, and here is a layout of it drawn to the scale. And then it was superseded by GRAPES 2, which was started nearly 30 years back. It was, as you can see, is much larger than GRAPES 1, more sensitive, and it had a muon detector. GRAPES 1 did not have muon detector. And finally, it culminated with the construction of GRAPES 3 experiment, which is our most sensitive instrument. And this is the layout of this experiment, and it has a very large 560 square meter area muon detector. Now, here is a view of the GRAPES 3 experiment. It is a collaboration of Indian and Japanese groups, and that is why you see our flags and Japanese flag here. And these halls you see on the left center are the components of the muon telescope. And these white cones you see are plastic scintillator detector. Here is a list of 12 institutions which are part of the GRAPES 3 collaboration, along with the name of scientists who are working on this experiment, and there are nearly 30 of them. Now, what is the objective of this experiment? Well, we would like to study universe at high energies, as I said in the beginning, and that is because acceleration and propagation of high energy particles requires extreme conditions, and one hopes that such extreme conditions, if they are studied properly, may reveal new physics or new science, and that is the primary objective. And for that, we basically study in terms of 4 different domains. Number 1, we study acceleration of particles in atmospheric electric field, where particles can be accelerated to as high as a giga electron volt. And when I talk about atmospheric electric field, I am referring to thunderstorms. It's hard to believe that thunderstorms can accelerate particles to GeV energy, but indeed it happens, and we have evidence of that. And thunderclouds can have size going all the way from 1 kilometer to 10 kilometers. Next is the study of solar storms, where we study coronal mass ejections, and energy can be as high as 10 GeV, and the size of your accelerator is basically the size of the solar system. Next, we also study galactic cosmic rays, which, as the name implies, are the cosmic rays produced within the galaxy, and the energy involved is nearly 1,000,000 times higher at about 10 raised to 6 GeV, and the scale is the size of our galaxy itself. And the final topic is the study of diffuse multi-TeV gamma rays, where we can probe primary cosmic rays of energy as high as 10 raised to 11 GeV, and these are the highest energy cosmic rays that are known to exist in nature. And here one is probing a scale of nearby universe extended to say up to 50 million light years. Now, the Grapes 3 experiment itself consists of two major components. You see these white cones, each one of them is a 1 meter square area plastic scintillator detector. And I would show you in a minute how does the plastic scintillator detector works. And then there is this 560 meter square muon detector, and you see these 4 squat buildings. Each of these buildings are comparable to a small auditorium in any college or institution, and it houses a muon detector of area 140 square meter. Altogether it makes it for a total area of 560 square meter. The threshold for detection of muons is 1 GeV, and UT is located at this geographical location 11 degrees north. So, it is very close to equator. Here are some references to papers that have been published describing the details of this experiment. Now, I mentioned at the beginning of this talk that if you want to do new science, it is important to do something which has not been done before, which means you must use an instrument which has not been used before, or deploy in a manner which has not been deployed before. And the capability of your instrument depends on the technology that is available to you. As the technology advances, our instruments advance, and we get higher sensitivity, and we are in a position to make newer and better discoveries. So, here I am going to give you a very brief summary of some of the indigenous technology development that we have carried out for the Grapes 3 experiment. Now, what you see here, the bluish colored slabs of plastic, these are plastic sheets which are nearly a meter long and an area of 70 centimeter by 100 centimeter and a thickness of about 4 centimeter. And you see, when you look through this sheet of plastic, you can actually see end to end. If I place a newspaper at the other end of the plastic scintillator, you can read what is written. Try doing that with a sheet of glass, the best quality glass, and even if the glass is 10 centimeter thick, you cannot see anything. So, this has very high transparency, and this is not something that we developed for the first time, but we did develop for the first time in India with properties which are comparable to the best scintillator that are available globally. But the best part is it was done at a cost which was about a third of cost of importing these things. And these instruments are now being used by more than a dozen collaborating institutes of Grapes 3 experiment. Here you can see this sheet of plastic which I am holding in my hand, and this is when we assembled it in form of a square meter area muon detector. And below on the left you see the light output of this scintillator when a muon goes through it, and what you see are actually two plots. The one in black is the data that we gathered when a muon passed through this plastic scintillator, and the dotted blue curve represents the result of a computer simulation of this detector, which exactly reproduces what we measure in reality. And similarly, on the right you see the measurement and simulation in terms of time profile of this signal, and we could perfectly reproduce, and these are the two most important properties of a plastic scintillator. So, what is the advantage of doing all this? Well, if you can model a detector in your computer, it is a lot easier to design a detector. You can change your computer model and redesign so that it meets your requirement. But if you have to make a prototype, it costs a lot of money and it takes a lot of time. So, this is a paper where all these simulation results are presented. If you are interested, you can go through them. And we have in fact used this computer model to design detectors for ourselves as well as for others. Now, I was talking about all these particles which are moving at speed of light, and if you want to record and process the signal, you have to also work at speed of light. That means you need fast electronics. And this is some of the circuitry we developed, including an amplifier with a large gain, which can record the arrival time of these particles with a precision of 90 picoseconds. And remember, 90 picoseconds is a very short time in which light travels only 2.7 centimeters. And we also developed what I would call a stopwatch. If you are measuring these particles and you want to find out what was the time interval between the particles that were received by different detectors, you need a device which acts like a stopwatch or which can measure the time of each one of those particles. And that was developed in collaboration with a scientist from Europe, and it works very well. And again, the cost advantage is huge. We could do it at less than a tenth of the price of importing this equipment, and these results have also been published. But money is not the only criteria. You see, when you are running an experiment, you do not know in astronomy when an interesting event will occur, as you would see shortly. And if an interesting event occurs and your instrument is not working, then you have lost it. You may have waited years to discover that event. And that is what happens when you use imported equipment, because sometimes they go bad and then you have to send it for repairs. It takes a long time, costs a lot of money. But if you have made it yourself, there is no problem. You can repair it immediately, or you can have a spare module which you can put it, and your experiment can run without any interruption. And that is the greatest gain of having indigenous technology. So now let's turn to the muon telescope, which I have been talking about it from the beginning. And this is the world's most sensitive muon telescope. What you see are four squat buildings in the background. And as I already mentioned, each has an area of 140 square meters. And if you look inside the muon telescope in the bottom of this picture, you see two modules, one on the left, one on the right, and there are similar two modules behind. So a total of 4 modules are there in each of these, what I would call a super module. Now, if you look closely, there is concrete at the bottom, and then there is a layer of tubes which is running in one direction, and then there is another layer of concrete, and there is another layer of tubes running in the perpendicular direction, and there are 4 such layers, and there is lots of concrete. So these tubes actually, I would like to share with you how these were made. So these are large tubes, 600 centimeters long, 10 centimeter by 10 centimeter in cross section, and these tubes are being cut in our workshop to size, and thereafter they are cleaned with high pressure water jet, dried, and once it's ready, its ends are sealed by welding thick plates, and these plates have a hole in the center to put a hermetic seal through which a 100 micron or 0.1 millimeter diameter tungsten wire is placed and strung. This central wire is insulated from the outer shell because of the presence of the seal, and so this acts as a proportional counter. So you apply a large positive potential to the central wire of about 3000 volts, the body stays at ground potential, and you fill it with a special mixture of gas. So when a muon passes through it, it produces a signal. Now the challenge was that we have to make this detector which is leak tight. So here we are testing, one of my colleagues is testing the performance of this tube to see if it has any leaks, and here's our team which is painting it to make it rust proof. And here you can see a stack of these proportional counters is being tested. And at the bottom right, you see the performance of this counter. You see a beautiful broad peak which is produced due to passing muons. And then you see 2 small peaks. You see these tubes are made up of iron. Okay? When a muon passes through this iron, occasionally it can knock out an electron from the K shell or the innermost shell of iron, and then electron from a higher orbit will jump into the K shell, producing a photon of 6.4 keV. And this 6.4 keV photon, which is actually an X-ray, gets detected by proportional counter, and because it's a monoenergetic X-ray, you get a sharp peak due to iron, which is labeled Fe. And similarly, the tubes have been coated with zinc to prevent rusting, and you see a zinc peak which is at 8.6 keV. So not only we can detect muon peak, we can also detect iron and zinc lines, which tells us what this proportional counter is made up of. Does it remind you of something? It's rather like what Archimedes was asked to do, to find out if the gold that the king had was all pure or not, and he did it by finding density. But you can still fool somebody with density, but you cannot fool by their atomic properties. So, if for example, it had contained some aluminum or some other material, we would see corresponding X-ray emission, and we would know what elements have gone into making this proportional counter. Now, you see, the interesting point is that we needed to make 3,800 of these. That is a large number. Now, we do not want them to give trouble. So, we designed them so that they will last at least for 30 years. So, how do we test? Well, we did certain tests, and I am not going to get into details of those. If those of you are interested, are welcome to visit our laboratory, and we will explain to you how exactly we did that. But the challenge is like this. You know, we all use cooking gas in our homes, an LPG cylinder, which contains about 14 kilograms of gas. Now, if I ask you that you put away this cooking gas cylinder for next 30 years and come back and measure after 30 years if any gas has leaked, your gas that has leaked should be less than 1 gram out of 14,000 grams. That is the challenge that we had, and we were able to meet that challenge. So, all these proportional counters actually are not the ones which went into making these old muon detector. That was done long back. These are actually going to make this new muon telescope, where you can see 80% of the work has already been completed, and when complete, it will have a coverage of the sky nearly 70 times larger than the old muon telescope. The old muon telescope is already best in the world, and this will give us an additional capability. It will do a much better measurement on everything that we do, and that is why we are constructing it. So, we hope with this new telescope we will be able to make new discoveries. So, now let us come back to our primary objective that we started with, and that is to study a universe at high energies. Now, I have 4 topics listed here, and if I want to go through each one of them, it will take several hours. So, I would just skip the other 3 topics. I will just focus on one topic which has created a lot of excitement in worldwide scientific community as well as among general public, and that is the topic of solar storms and coronal mass ejections. Okay. And I already showed you, this is the main instrument that we use, the muon telescope with a total area of 560 square meter, and these tubes are actually the ones which give us the direction of muons. And how do they do that? It is very simple coordinate geometry. So, you see, here is a view of one of those 2 layers. If a muon goes through, let us say, the counter here which is labeled 0 and the one below it, that means the muon is vertical. And if it goes through this proportional counter and the one here labeled 6, then you see it is an inclined muon. Now, we know the coordinate of each of these proportional counter, and from that we can determine the direction of the muon in this projection plane. And similarly, we have a projection plane in the perpendicular direction, and by combining this information we can make a sky map which is shown on the right. We basically use a matrix of 13 by 13, so we can divide up the sky into 169 directions. These of course have been for reasons which I am not going to get into, are combined into 9 directions which are labeled vertical: north, south, east, west, northeast, northwest, southwest and southeast. You may wonder why this peculiar combination. Well, by this combination we get approximately equal solid angle in all 9 directions. So, this is how the telescope works, by using the pattern of hits in the proportional counters. Now, before I turn to scientific results, I would like to share with you the sensitivity of this instrument. You see on this plot here, what is shown is the atmospheric pressure in Uti measured over a period of 7 days, expressed in units of hectopascal, and you see the pressure shows beautiful sinusoidal variation. Okay. And if you look at the muon intensity, that also shows a similar variation with a period of 12 hours. Now, you wonder why this is varying with a period of 12 hours. This is actually a very well known phenomena which was originally attributed by Newton to be due to atmospheric tides. Just as we have tides in the ocean, he expected atmosphere being a fluid would also have tides in the ocean. But eventually it turned out it was not Newtonian tides, it was something different. But nevertheless, this 12-hour periodicity is present. So we use this 12-hour periodicity and apply Fourier transform and extract the dependence of muon intensity on pressure. And this is what is shown on the bottom right hand plot. And you see there is a beautiful dependence of muon rate on atmospheric pressure. From that we can derive the pressure coefficient of minus 0.128% per hectopascal. Now this is just a number. What does this number mean? Well, the muon detector is sitting on ground. Now I am sitting in front of you. Now do you know the atmospheric pressure near your feet or my feet is higher than the atmospheric pressure near my head? Now normally we don't worry about that because it's so tiny, but not for this muon telescope. If the height of this telescope was just increased by 1 meter, the intensity of muon will change so dramatically that it will cause a 5 sigma change in terms of significance of the muon intensity. This result was published in this paper, which is listed here, and you can read it if you want, if you are interested in more details. So this is how sensitive this instrument is. A very tiny change in atmospheric pressure causes its intensity to change. And that's important because you want a sensitive instrument. Well, what about the atmospheric temperature? Now, as you know, atmospheric temperature, not at the surface of the earth, but in the upper atmosphere where the muons are produced, remains almost constant during a day or during 24 hours, but it changes gradually over seasons. So you see the blue plot at the bottom of this figure. You see it undergoes cyclical variation. Its maximum around day 200, which is June of the month. This is data of 6 years going all the way from beginning of 2005 to 2010. It increases, decreases and so on. It has an amplitude of about 1 Kelvin, very tiny. And this is the muon intensity over the same period. It again shows similar cyclical variation. And again you apply Fourier transform, you get this kind of dependence on the plot in the right. And from this we can determine the temperature coefficient, which turns out to be minus 0.17% per Kelvin. And what is the significance of this result? Even if atmospheric temperature changes by 0.3 degrees, it dramatically alters the muon flux. So this is what gives us the capability to study interesting phenomena, which now I am going to describe to you. So what happened on 22nd June 2015 was that a massive solar storm occurred on the surface of the sun, resulting in a coronal mass ejection, which led to emission of 10 raised to 10 tons of plasma. That's a massive amount of plasma. Now it's easy to put a number like 10 raised to 10 tons, but if you want to put it in context, if you took every single building in our country and converted it into plasma, that's how much plasma you would produce. The total energy contained in this plasma was 10 raised to 33 ergs. That is enough energy to supply all of Earth's needs for everybody for the next 100,000 years if we continue with the present level of consumption with present population. So it's mind-boggling number. Now what happened? You see there is a satellite which is placed at a distance of 1.5 million kilometers from Earth in the direction of Sun, which acts as our warning that a solar storm is on its way. And that satellite detected that solar plasma, which normally travels at a speed about 400 kilometers, which you can see here on the top of this plot, suddenly jumped to above 700 kilometers per second. And this is known as a shock front. So it jumped by nearly 300 kilometers. And just as it went up, you see the magnetic field, which is around 10 nanotesla, jumped up to nearly 50 nanotesla. And what is even more remarkable is the Z component of magnetic field, which happens to be in the north-south direction, went south. Okay. And its amplitude was 40 nanotesla, almost same as the total magnetic field. So the magnetic field was oriented opposite to Earth's magnetic field. And just when all this happened, Graves 3 muon telescope registered a sudden increase in muon intensity. So this is very interesting. So you see the information we are getting is from a point called Lagrange point 1 or L1, which is 1.5 million kilometers from Earth. And the plasma, which started out with 1,400 kilometers per second speed, slowed down to about 700 kilometers per second. It would take another half an hour to reach the Earth. But of course, the satellite could relay its information by radio, which would arrive in about 5 seconds. So, this was very interesting. Now, these, since they look very similar, we said, okay, let's look how similar they are. We inverted the polarity of the magnetic field, which is shown here. And the muon intensity is shown in blue, and the red is the Z component of the magnetic field. And you see they are nearly identical. They are 94% identical. And the significance of this result is 54 sigma. This result we publish in this paper here. And it happened on 22nd June 2015. The peak of it happened at midnight. Now, to put this 54 sigma in context, let me tell you, when the Higgs boson was discovered nearly 7 years back, there were 2 experiments that reported 2 5 sigma detections. And similarly, when 3 years back gravitational waves were discovered, they also reported 2 detections of 5 sigma each. But this is a detection of 54 sigma, but it's much more than that. You remember, we have 4 supermodules. If you look at each supermodule, we have 27 sigma coming out of each supermodule. So, these are 4 independent instruments giving us massive result. And this is exactly what you expect. If you divide your data 4 times, your significance will go down by square root of 4, that is 2, and that is what you see, 27 sigma. Well, but each of these telescopes has 4 modules. Let us look at those 16 modules. You see, all 16 of them show. So, these are 16 independent measurements, each is about 13 sigma. But remember, this is a telescope, so it looks in 9 independent directions. So, let us look at each telescope and its 9 independent directions. So, we have 144 measurements, 42 of them are more than 5 sigma. So, there is, I think I have convinced you by now that there is no doubt that this is a real event. Well, now let us go back to 9 directions. And this is how the event looked in 9 different directions. You see, this intensity is not same in all directions. And it puzzled us what caused this event to occur in the first place. But there is a very strong clue, and that is magnetic field. So, we said, well, if the magnetic field was opposite to Earth's magnetic field, then obviously it will weaken the Earth's magnetic field. The Earth's magnetic field acts like a dipole, very similar to the bar magnet that I am holding in my hand, with north pole shown by a white dot here, and this is the south pole. Now, if I bring this magnet close to a piece of iron, which is the yellow piece here, as we get close to it, because of the magnetic field, it picks up the iron bar. Now, what happened during the solar storm was the magnetic field of the storm weakened Earth's magnetic field, because that magnetic field was oriented in a direction opposite to that of Earth's magnetic field. So, let us do the same experiment. We will bring another magnet where north pole is here, and now we will bring it close to the south pole of the first magnet. As we bring closer, the magnetic field of the first magnet is getting weaker and weaker and weaker, and now when we brought it together, the magnetic field is completely destroyed and the piece of iron falls down. And this is exactly what would have happened when the solar storm struck. Of course, the Earth's magnetic field did not get destroyed fully, it only got weakened, but you get the idea. Now, as you all know, Earth's magnetic field is our first line of defense against incoming radiation. What it does is it bends incoming particles, cosmic rays, back into space and does not allow them to enter the Earth. Nearly 99% of them are sent back. 1% of them, which are above a certain minimum energy, do manage to reach the Earth, and that energy depends on the direction. For example, in northwest direction, that minimum energy or threshold is 16.1. In northeast direction is 23.5. These are very different. So, what we postulated, it is the magnetic field that is responsible for producing this effect. So, we did actual computer calculation and found what will be the effect in each of these 9 directions. We found, yes, indeed, you would produce such an effect, but the amplitude that we calculated was almost 20 times smaller than what we actually observed. So, this was a puzzle. 40 nanotesla obviously is not enough to explain this effect, because the Earth's magnetic field is nearly 40,000 nanotesla at UT. So, how do you produce an effect which is about 1% from a cause which is just 40 nanotesla, which is 0.1%. So, we next examine, if we increase this magnetic field somehow, we don't know how it would have increased. If we increase this magnetic field by a factor of 2, 4, 8 or 10, then what happens? We found the intensity of this effect scales with the magnetic field. And so then once we knew this, we could actually fit the data, but we required an enhancement of magnetic field by a factor of 17 to 680 nanotesla, and that is what is shown in dotted curve. And now you can see this calculation almost exactly reproduce what we are observing. For example, the amplitude is higher in the north and smaller in the south. And so the fact that Earth's magnetic field became weaker could explain all the observations almost completely. Not only that, remember this event was observed at midnight, and this is a view from the pole and this is the equatorial view, and the particles, you see, basically what happened was that as the magnetic field of the Earth became weaker, this threshold which was 16 got reduced, and here is a calculation of how much reduction happened in the three directions, that is the north direction, the central direction and the west and the south directions. And you see the decrease was larger in north, and that is why you see larger amplitude in north, and it was progressively smaller as you went south, and that could explain. So basically what happened is lower energy cosmic rays which otherwise would have gone back into space started entering our atmosphere. As you see in this picture, this is a view of the cosmic rays which entered due to lowering of the threshold due to the coronal mass ejection or the solar storm. And these were low energy cosmic rays which were bent by Earth's magnetic field. They started from the day side of the Earth, were bent around, and they entered on the night side, which can also be seen in the equatorial view here. You can see that they are coming. These are representation of 9 different directions, and they are entering here at Uti, and because of this bending they appear to come in night time, even though they actually started out from day side of the Earth. So we could explain almost all features of this experiment. Now this work somehow created a lot of excitement worldwide, and this was because of sequence of events which had nothing to do with our measurement that had happened before us. There was an article in Science with a title, Here is how the world could end and what we can do about it. And it lists the major threats to human civilization. Number 1 threat is solar storms. Number 2 is cosmic collision of an asteroid or comet landing. And number 3 is super volcano. Now there is very little you can do about threat 2 and 3. But there is something you can do about threat 1, that is solar storms. So why solar storms are dangerous? And that is because in a solar storm you produce large amount of ionization. And because of this lowering of threshold of cosmic rays that can reach the Earth, they manage to enter the atmosphere, and cosmic rays are charged particles, they cause ionization. Now you see, normally we transmit high voltage power across long distance by using these high voltage transmission lines, but the real insulator for these transmission line is the air, because the wires are separated by several meters, and it's air that acts as insulator when you transmit power at say 440,000 volts or even higher voltage. But imagine if solar storm were to occur and it were to cause large ionization, then the air will become conducting, and that will short circuit these transformers, and it will plunge the entire society into a complete blackout. You would lose these high voltage transformers. So nothing will happen to human beings, but we'll go back to Stone Age. That is what this article is trying to explain. Now following this article, there was a executive order by the President of the United States directing all their agencies to prepare for dealing with such events, because their worry was that advanced infrastructure system and technologies such as GPS, communication, satellite operation, aviation and power grid could all suffer serious damage during an extreme solar storm event, and that's something that they are worried about. And this is not science fiction, this is something that has happened in the past and could happen in future. When it could happen, nobody could say, but it could happen. So the important thing is to prepare. So what is the protection that you have? So I'll tell you in a little while. But continuing with the sequence, our paper appeared a week after the executive order of President of the United States, and where we talked about transient weakening of Earth's magnetic shield probed by cosmic ray burst. And I would just read the last sentence of this abstract. The simultaneous occurrence of the burst in all 9 directions suggests its origin close to Earth. It also indicates a transient weakening of Earth's magnetic shield and may hold clues for a better understanding of future superstorms that could cripple modern technological infrastructure on Earth and endanger the lives of astronauts in space. So this was basically was a sequence of events that happened. Now, what is the protection we have? The only protection against a solar storm is that you shut down everything, have a global shutdown. That's the only way you can overcome. Let the solar storm pass, and then you can switch back on when the ionization has disappeared from our atmosphere. Okay, so this work created huge amount of excitement. There was worldwide coverage of our work in nearly 119 countries. There were 24 YouTube videos. I would like to share one of these at the end of this presentation. And there are more than 1,000 reports in 37 languages. So instead of listing all 119 countries, what we decided to do is paint the world map into the colors of our flag. So wherever there was a report, we painted it in saffron, white and green, and where there was no report, we left it in black. And all these reports in form of 6 volumes are available at our web page, which is listed here. Those of you who are interested can go through it and learn more about it. This is a partial list of the YouTube videos. The work on solar storm based on Grape's 3 muon telescope attracted considerable worldwide attention. There was coverage in 119 countries, where in more than 1,000 reports have been published, and in 37 different languages. And here I am holding the first volume, which contains some of the reports in English language, and there are reports in other languages as well. And all of these have been compiled in form of 6 volumes, which are also available on our web page, which you are most welcome to visit and explore for yourself. Thank you. Okay, so this is as far as what work was done. Now, this is nearly 2 years back. What is the present status? So, I would like to share with you some of the developments that have happened since that time. So, one of the things which we realized early on, that solar storms have potential to disrupt human life. So, they are a subject of great deal of interest to all of us. Now, what can an experiment like Grape's 3 can tell which satellites cannot? And this is something very interesting. So, I would come to that in a minute, but as I already mentioned, that you would want to have a global shutdown in case an extreme event occurred. Now, at present, Grape's 3 studies solar storms with highest sensitivity, but the data is analyzed post facto, that is after the event. We do not even analyze it in real time, and that is a limitation at the moment, but that can change. We have carried out the analysis of existing 19 years of data, which indicates that about 40 solar storms have occurred, and 10 of which were fairly prominent events. They were not devastating events, otherwise we wouldn't be here to talk about it, but they are fairly prominent. But we have already identified 40. We hope that by the time we finish all our data analysis, we would have nearly 50 events. Now, the event of 22nd June showed a delay of 28 minutes relative to satellite prediction. You see, satellite is sitting at a distance of 1.5 million kilometers from Earth in the direction of Sun. That is L1, Lagrange point 1. So, once it makes a prediction, it does not know what happens to that solar storm as it approaches Earth. It only knows it has crossed L1. Now, our data showed that the event took an extra 28 minutes. The prediction was it should take 36 minutes, but it took 36 plus 28 minutes. So, it took actually 74 minutes. Now you may wonder why that is so important. I'll come to that in a minute. Now all these 10 events show delays that range from 16 to 64 minutes. So every one of them shows additional delay over and above what is predicted by satellite. The Grape Street data therefore indicate that Earth's magnetic field acts as a brake and slows down the progress of solar storm after it reaches the Earth's magnetosphere, that is the region where magnetic field is dominant. It thus provides a more accurate estimate of the onset of a solar storm. Now imagine if there is indeed an extreme event which leads to a global emergency and you need to shut down the power. Now if the satellite has predicted the solar storm should come after 36 minutes and it doesn't come for another half an hour, your economy has shut down for half an hour, which is avoidable, right? And I just calculated 1 minute of world GDP is about 1,000 crores. So if you can make more accurate prediction, you can imagine what kind of, not only in terms of money, in terms of disruption of life that it would save. At present, we are in the process of developing suitable software tools to estimate the delay. Right now we are doing measurement based on actual data, but what we want to do is to develop a model based on the storm parameters such as the magnetic field, its components, the shock speed, the compression of magnetosphere that occurs, which leads to enhancement of magnetic field, which I mentioned earlier, from a subset of data. So we aim to develop this model using part of the data, say out of 50 events, maybe some fraction, 70% of data. And then to test these predictions by using remainder of data, whether the model actually works. If the model works, then it will be possible for us, after receiving the information from satellite, to calculate and tell immediately when the storm will actually arrive. Well, in reality, it takes 5 seconds for data to come from satellite to Earth. If it is relayed immediately to us, it takes us about 1 second to calculate. Should take about 1 second to calculate its delay. And that will be a very useful thing if it could be done. So let me conclude by expressing my thanks, and we hope that you would enjoy the video which tells in popular language what all I described to you in more technical terms. Thank you.